I want you to imagine just for a second a very specific, um, like a very terrifying scenario.
Oh, the ultimate apocalyptic thought experiment. I know where you're going with this.
Right. So imagine you wake up tomorrow morning and one single element on the periodic table, element 14 to be exact,
Yeah.
has just completely vanished from the crust of the Earth, like poof, erased from existence.
Yeah, the cascade of failures from that would be, instantaneous. We aren't just talking about a minor technological setback here.
No, not at all.
Civilization as we know it would face a near instant structural collapse.
Exactly. When you look at the sources we're diving into today, these incredible notes from a project called The Architecture of Sand, the stakes become, well, horrifyingly clear.
Oh, absolutely.
It isn't just that your smartphone dies, though. I mean, it absolutely would. But the global internet infrastructure relies on servers and routers that would instantly just turn into dead weight.
Right, and think about the global banking system. It freezes in a microsecond.
Yeah. You couldn't buy groceries, you couldn't withdraw cash or verify a ledger. Modern electric vehicles just halt in their tracks.
And it gets worse when you think about hospitals.
The hospitals, yes.
They would literally go dark. Life-saving medical equipment, pacemakers, diagnostic machines, they would all simply cease to function.
It's terrifying. And the wildest part of this whole nightmare scenario, the element we are talking about, the one holding up the entire architecture of the modern world, is silicon, element 14.
Yep, good old silicon.
Which brings us to the core mission for today's deep dive. We're going to explore the central mystery of how something as incredibly ordinary, as completely ubiquitous as sand, became the invisible foundation of our digital world.
It is a phenomenal story.
Because, I mean, I look at a beach and I just see dirt and crushed rocks, you know? How on earth do we trick rocks into doing complex math?
Well, to answer how a rock does calculus, we first have to understand the true nature of this element, and it starts with what chemists call the abundance paradox.
The abundance paradox.
Yeah, so silicon makes up about 27% of the Earth's crust by mass. It is literally everywhere. You are standing on it right now.
Wow. Over a quarter of the crust?
Right. But here's the paradox. Despite being one of the most common things on the planet, it is almost never found in its pure elemental form in nature.
Because it's like incredibly highly reactive,
I know
right?
that.
It loves to bond with oxygen.
Oh, it desperately wants to bond with oxygen. When silicon and oxygen meet, they form silicon dioxide, which we commonly know as silica.
Okay, right.
And that is what quartz is. That is what ordinary sand is mostly made of.
So the sand on the beach is basically just silicon holding hands with oxygen.
Exactly. And it took until 1824 for a Swedish chemist, Jöns Jacob Berzelius, to actually figure out how to, rip the oxygen away and isolate pure silicon.
1824. That's surprisingly recent for an element that's everywhere.
It is. For almost all of human history before that, we just thought of it as a building material. We melted sand to make glass. We used crushed rock to make concrete.
Right, and the name itself kind of gives away how we used to view it.
Yeah.
I read it comes from the Latin word silex, which literally just means flint or hard stone.
Yeah, a rock for sparking fires.
Exactly. We used it to spark fires and build walls. But the secret to its modern power, like the reason it runs the internet, lies deep down in its atomic structure.
That's where it gets really interesting.
Yeah, because the sources point out that it exists in this weird chemical twilight zone.
Mm-hmm.
So we have metals like copper, which are fantastic conductors. Electricity flows through them like water through an open pipe.
Right, the path of least resistance.
And then we have insulators like rubber, which block electricity entirely. The pipe is capped off. But silicon doesn't neatly fit into either of those categories, does it?
No, it doesn't. It sits right on the boundary. Under normal conditions, silicon is actually an insulator. It doesn't want to conduct electricity.
Okay.
But if you introduce a little bit of energy, so heat, or a tiny electrical voltage, its atomic structure shifts just enough to allow electrons to flow. Yeah, and this property, this ability to switch, is why we call it a semiconductor.
A semiconductor. Okay, I was trying to visualize this while looking through the research. Is it fair to think of silicon like a bouncer at a nightclub?
A bouncer. Okay, I like where this is going.
Like a metal is just an open door, right? Anyone can walk in at any time. And an insulator is a locked door. The club is closed, nobody gets in.
Right.
But silicon is like the bouncer standing at the velvet rope. If you hand the bouncer a little cash, which in this case is, a tiny trigger voltage, they unclip the rope and let the electricity pass through.
That is a great analogy.
And then take away the trigger voltage, the cache, and the bouncer clips the rope back and the flow stops.
That holds up perfectly for a single microscopic switch, which we call a transistor. You apply a voltage to the gate of the transistor, the bouncer steps aside, and current flows through. You remove the voltage, the current stops.
Okay, but this is where I get stuck.
Yeah.
Having a microscopic bouncer is cool, but a single switch turning on and off doesn't really explain how my computer can, like, render a 3D video game or calculate a spreadsheet.
Right, one switch is just on or off.
Exactly. So how do we bridge the gap between one bouncer opening a door and a system actually performing complex logic?
Well, you do it by wiring those bouncers together in very specific physical arrangements.
Okay.
This creates what engineers call logic gates. Let's say you take two of your silicon bouncers and place them in a single narrow hallway, one right after the other.
So they're in the line.
Yep, in series. For electricity to get from the beginning of the hallway to the end, it has to pass both bouncers.
Okay, so if I only trigger the first bouncer to open the rope, the electricity just stops at the second bouncer.
Exactly. The only way current makes it to the end of the hallway is if you trigger bouncer A and D bouncer B.
Oh, an A&D gate.
You have just built an A and D gate. The physical circuit is making a logical decision.
That is wild.
Now, imagine a different hallway. This one splits into two parallel paths, with one bouncer guarding each path, before the paths merge back together at the end.
Okay, so in that setup, the electricity only needs one of the paths to be open.
Right.
So if I trigger bouncer A or bouncer B, the current gets through.
You've just built an OR gate. And by combining A and D gates, OR gates, and a few other variations, you can build a circuit that takes two electrical currents representing the number 1, runs them through a maze of bouncers, and outputs a current that represents the number 2.
Wait, so you have physically forced the rock to perform addition.
Yes, you are doing physical math. And if you string billions of these microscopic logic gates together, opening and closing billions of times a second, that rock isn't just adding numbers anymore.
Right, it's processing a video call.
Exactly. It is running an artificial intelligence model.
That completely demystifies it for me. Like, it's not magic, it's just incredibly complex microscopic plumbing.
It really is just plumbing on an atomic scale.
But, okay, to build a maze with billions of perfect microscopic bouncers, you need a flawless material.
Absolutely flawless.
And the sources emphasize that we can't just take a bucket of wet sand from a beach, melt it in an oven, and pull out a computer chip.
No, definitely not.
The material has to be altered at an atomic level to reach what they call 9 nines purity.
Yes, 9 nines. That's 99.9999999% pure.
I mean, if my math is right, that means for every 1 billion atoms of silicon, there can only be one single atom of an impurity, like one atom of iron or aluminum.
That's correct. 1 in a billion.
That level of purity doesn't even exist in the natural universe.
Huh.
I was really trying to wrap my head around how we physically do this, because taking sand and turning it into something that pure, it sounds like modern alchemy.
Well, the engineering required is staggering. You start with high-grade silica sand and throw it into a giant arc furnace with carbon, heating it to thousands of degrees.
Sounds intense.
It is. The carbon bonds with the oxygen in the sand and burns off as carbon dioxide, and that leaves behind metallurgical-grade silicon.
Okay, so now we have pure silicon.
Not quite. That is only about 99% pure.
Oh.
And to a microchip, 99% pure is basically garbage.
Right, because those remaining impurities are like rogue bouncers in our hallway, right?
Exactly.
If there's a stray iron atom in the middle of our logic gate, it might let electricity leak through when the door is supposed to be shut.
And the entire mathematical calculation breaks down. One leaked electron in the wrong place can literally crash a system.
Wow.
So we have to take that 99% pure, solid silicon and put it through a process that seems, honestly, completely counterintuitive.
What do we do?
We turn it into a liquid and then a gas.
Wait, we vaporize a rock.
We do. We react it with hydrochloric acid to create a compound called trichlorosilane. We distill that liquid repeatedly the same way you would distill alcohol to boil off the impurities.
That is insane.
Then, we vaporize it and deposit those perfectly clean silicon atoms onto a heated rod in a vacuum chamber. Slowly, atom by atom, a giant crystal of ultra-pure silicon grows.
Atom by atom, we turn a solid rock into a gas and rebuild it just to make sure there isn't a single speck of dust in it.
That's what it takes.
It's just breathtaking. And, once humanity figured out how to achieve this flawless semiconductor-grade purity, It triggered the most aggressive technological explosion in recorded history.
Oh, without a doubt. It gave birth to the transistor.
Right, because before the silicon transistor, the only way we had to control the flow of electricity for computing was using vacuum tubes.
Ugh, vacuum tubes. They were essentially modified light bulbs.
Yeah.
They were massive, they generated extreme amounts of heat, and because they relied on these fragile physical filaments inside a glass vacuum, they burned out constantly.
I read that the earliest room-sized computers, which by the way had less processing power than a musical greeting card today,
Yep.
they required a small army of technicians.
Just to keep them running.
Yeah, literally running around replacing blown vacuum tubes before the machine could finish a single calculation. It was like a giant fragile plumbing system made of hot glass.
Exactly. And the transistor replaced that entire fragile hot glass bulb with a microscopic solid block of purified silicon.
No vacuum needed, no glowing filaments.
No moving parts at all. It was unbreakable. Now, it's worth noting that the very first transistors were actually made of a different semiconductor material.
Oh, germanium, right.
Yes, germanium.
So why did element 14 win? Like, why aren't we living in the germanium age right now?
Two reasons. Heat and rust.
Heat and rust.
Yeah, so germanium is a fantastic semiconductor, but it has a lower heat tolerance. When germanium circuits get warm, they start leaking electrons.
Ah, the bouncers get tired and just let everyone into the club.
Perfect way to put it. Silicon requires much higher temperatures before it loses its structural integrity.
And what about the rust?
Right. So furthermore, when silicon is exposed to oxygen, it forms a perfectly uniform layer of silicon dioxide glass, which acts as a brilliant natural insulator to protect the tiny circuits.
Oh, that's convenient.
Very. Germanium's oxide layer, on the other hand, is water-soluble.
Wait, it dissolves.
It literally washes away. So silicon was the clear, durable winner.
That makes total sense. Which leads to a really profound shift, not just in technology, but in geography.
Geography.
Yeah, because we usually talk about this technology on a microscopic scale, atoms, nanometers, tiny logic gates, but mastering element 14 literally reshaped the map. It created an entire geographical region defined by this one single element, Silicon Valley.
Oh, absolutely. Throughout human history, regions of extreme wealth and power were defined by what they could extract from the earth to burn or build with.
Right, you had coal mining towns in Appalachia, steel cities like Pittsburgh, the gold rush territories.
Exactly. But the empire of Silicon Valley was entirely different.
It was an empire built on extracting logic from a rock rather than extracting energy from it.
That is a beautiful way to phrase it. It decoupled massive economic power from the ownership of rare, raw physical resources.
Because sand is everywhere.
Sand is everywhere. The power shifted to whoever possessed the intellectual property, whoever could design the microscopic architecture to etch the smartest, smallest lines into a piece of melted sand.
And we figured out how to print billions of these tiny silicon switches onto a single flake of material the size of your fingernail.
The integrated circuit.
The integrated circuit.
Yeah.
And that explosion of miniaturization brings us to where we are today. Because, Silicon Valley started the revolution, but silicon has completely escaped the computer lab.
Oh, it's everywhere.
It is the invisible foundation everywhere, all at once. If we look at the high-tech brains first, the sources list out these cutting-edge uses. It's the CPUs running your laptop.
The GPUs rendering hyper-realistic video games.
Yes. The memory chips storing decades of family photos. It's the massive AI processors in giant data centers that are currently teaching machines how to speak, write code, and diagnose diseases.
It is the core of quantum computing research. It's the brains of satellites orbiting the Earth and the rovers exploring the surface of Mars.
It's unbelievable.
Yet, that digital universe is only half the story.
Really?
Because silicon is also the absolute backbone of the physical industrial world, particularly when you look at the renewable energy sector.
Okay, I think I know where you're going with this.
Think about a solar panel. A solar panel is largely made of silicon, but it isn't using its semiconductor properties to do math.
Right.
It is using them to catch sunlight and convert it directly into a flow of electricity.
Wait. So it's doing math in my phone, but generating power on my roof. How does the exact same material do two completely different things?
It comes down to what we call the photovoltaic effect, and it relies on that exact same bouncer property we talked about earlier.
Okay, tell me more.
In a computer chip, we use an electrical voltage to tell the bouncer to step aside and let current flow.
Right.
In a solar panel, the trigger isn't an electrical voltage, it's a photon of light from the sun. The solar panel is made of two slightly different layers of silicon. When a photon smashes into the silicon atom, it imparts just enough energy to knock an electron loose. And because of the way the layers are structured, that loose electron is forced to flow in one specific direction, creating an electrical current.
So instead of a battery pushing electrons through the bouncer to do logic, the sun is physically punching electrons out of the bouncer's hands to create power.
That is a highly visceral but surprisingly accurate way to picture it.
I love that.
And beyond solar energy, we are still using silicon in its less refined forms everywhere.
Like where?
It is the primary component in the glass windows of your house. It is a critical binding agent in concrete, asphalt, and ceramics.
Wow.
It's used in life-saving medical devices and the structural alloys of the aerospace industry.
So the concrete in the foundation of my house, the solar panels on my roof generating the power, and the AI processor in my phone.
They are all leaning on the exact same element from the periodic table.
The exact same one.
The versatility is just unmatched. I mean, we are asking this one element to serve as the raw material for our most basic physical shelters and simultaneously the raw material for our most advanced digital minds. It is doing a lot of heavy lifting for humanity.
But of course, carrying the weight of the entire modern world comes with a heavy footprint.
Oh, definitely.
The hunger for more chips, more data centers, more processing power, it is completely insatiable.
And that brings us to the stark cost of progress. Because while sand itself is cheap and abundant, the process of turning it into that 9/9 ultra-pure semiconductor, it is brutal on the environment.
Right. The sources talked about these manufacturing facilities, fabs.
Yes, fabrication plants, or fabs, they require astronomical amounts of resources. The sheer electrical energy needed to heat those arc furnaces to thousands of degrees is massive.
I can imagine.
But the most surprising footprint is actually water. Fabs require millions of gallons of water every single day.
Wait, I have to push back on that because that seems completely counterintuitive.
How so?
We just spent 20 minutes talking about how carefully we have to control the flow of electricity on these chips. Aren't water and electronics a notoriously terrible combination? Like, why are we dumping millions of gallons of water onto microchips?
Well, we aren't using normal water. We're using ultra-pure water, or UPW.
Ultra-pure water.
Yeah. Normal water is terrible for electronics specifically because it is full of dissolved minerals and salts, which conduct electricity and short out circuits.
Right.
But in a fab, they filter the water until it is literally nothing but H2O molecules. No minerals, no bacteria, no stray ions.
Oh, I see. Because if a microscopic speck of calcium from normal tap water dried on a silicon wafer, it would be the size of a boulder compared to a transistor.
Exactly. It would smash the logic gate.
That makes total sense.
And ultra-pure water is actually incredibly aggressive. Because it has been stripped of everything, it is hungry to absorb any rogue atoms it touches.
Like a sponge.
Yes. Fabs use it as the ultimate solvent. Between every single chemical etching step in the manufacturing process, they wash the silicon wafers in UPW to strip away any stray molecules, ensuring absolute, flawless purity. But creating millions of gallons of UPW daily requires massive energy and really strains local water tables.
So we have this marvel of technology, this melted sand doing our thinking for us. But the reality of sustainable chip production is becoming a massive bottleneck.
It's a huge challenge.
Which makes me wonder about the future. Reading through the future technologies and the sources, the demands are only going up.
Exponentially.
Right. Artificial intelligence, robotics, autonomous vehicles, they require vastly more processing power than we can currently produce. And I saw mentions of researchers moving away from electrical silicon entirely and looking at photonic chips.
Oh, photonic chips are one of the most promising frontiers. Instead of using silicon to direct the flow of electricity, which is moving electrons, photonic chips use silicon structures to direct the flow of light, moving photons.
Okay, but wait. If light doesn't generate heat like electrons do, and light travels at, well, the speed of light, why didn't we just build computers with light in the first place?
That's a great question.
Like, why did we waste the last 70 years messing around with electricity?
It comes down to the brutal physics of materials science. Electrons are incredibly small, and we figured out how to build microscopic silicon gates to herd them around relatively easily.
Right, the bouncers.
Photons, waves of light, are physically much larger in terms of their wavelength. You can't just squeeze a beam of light through a 2-nanometer transistor.
Because it just won't fit.
The light wave is literally too big, it just scatters. It took decades of advanced research to invent nanoscale metamaterials and specialized silicon waveguides that could actually trap and bend light on a microscopic chip without losing the signal.
Ah, that makes sense.
Yeah.
We had to build a completely different kind of microscopic maze.
Exactly.
I also read about neuromorphic computing and the sources, which sounds like something straight out of a sci-fi novel.
It really does.
Yeah.
Essentially, it's trying to redesign the physical architecture of silicon chips so they mimic the neural pathways of the human biological brain.
Because our brains are incredibly efficient.
Unbelievably efficient. Our brains run on roughly the same amount of power as a dim light bulb, yet they perform real-time processing that would require a warehouse-sized supercomputer.
That's staggering.
So, by restructuring silicon away from rigid logic gates into flexible artificial synapses, we hope to capture some of that biological efficiency.
Okay, but even with photonics and neuromorphic designs, aren't we eventually going to hit a hard physical wall with element 14?
We are rapidly approaching that wall right now, actually.
Really?
Yeah, it is a limitation imposed by quantum mechanics. For decades, Moore's law held true. We just kept shrinking the silicon bouncers smaller and smaller, fitting more of them onto a chip to get more computing power.
Right.
But today, the velvet rope of a transistor is only a few silicon atoms wide.
And when you get down to the scale of individual atoms, the normal laws of physics stop applying, don't they?
They break down completely. We hit a phenomenon called quantum tunneling.
Quantum tunneling.
If the silicon barrier is only 2 or 3 atoms thick, the electron doesn't wait for the bouncer to open the door. According to the Heisenberg uncertainty principle, the electron just teleports right through the solid wall.
It just phases through.
Yep.
The bouncer becomes useless. The logic gate fails. Once we hit that absolute atomic floor, silicon to take us no further.
Wow.
We will have to transition to entirely new materials like graphene or carbon nanotubes to keep shrinking our technology.
Which brings us full circle, really. We started this deep dive with a thought experiment about a world going dark without element 14.
We did.
And what we've uncovered is the story of an incredible, almost unbelievable transformation. We took the most abundant, unremarkable stuff on the planet, ordinary sand, quartz, dirt, and through sheer human ingenuity, we figured out its secret atomic nature.
It's quite a legacy.
We learned to purify it to an impossible degree, to vaporize it and rebuild it atom by atom. We manipulated it into microscopic bouncers that control the flow of energy, and we strung billions of them together to trick rocks into doing complex math.
We built an entire age of human history on top of it.
Next time you look at a beach or, you stare at your smartphone, I want you to remember what you were actually looking at. You were looking at ordinary sand that humanity taught to think.
You are holding a piece of the Earth's crust that we polished and refined until it became the literal foundation of the digital world.
It is a profound realization. And, it leaves me with one final thought, something to mull over that really underscores this entire journey.
Good so.
We spend so much time today marveling at the invisible digital minds of artificial intelligence.
Oh, sure.
We talk about the cloud, the metaverse, algorithms, all these things that feel totally weightless, ethereal, and disconnected from reality. But we completely forget that this entire digital universe is housed in a very physical, earthly body.
Right.
The cloud is heavy. It is made of ultra-purified melted rocks requiring massive amounts of water and power.
Wow.
And as AI keeps growing exponentially, demanding more processing capability and more physical space, will the absolute physical limits of sand eventually become the ultimate ceiling for artificial intelligence?
Oh, that's heavy.
We are dreaming of infinite digital horizons, but we are doing it entirely on a foundation of rocks.
Wow. That is a truly wild thought to leave on. The infinite dreams of a digital mind, trapped inside the physical limits of a grain of sand. Well, that is all the time we have for today. Thank you so much for joining us and taking the plunge into this deep dive. Keep questioning the ordinary things around you, and we'll see you next time.